Okay, next up, question 5, part A says find the Cartesian equation for the curve r equals 4 cosine theta. And there's a hint here that says multiply both sides by r first. Okay, well, again, appealing to these relationships between polar coordinates and Cartesian coordinates, the nice thing about multiplying both sides of this equation by r as our first step is that we're going to get an r squared on the left side, and that's x squared plus y squared, and on the right we're going to get a 4 times r cosine theta, and r cosine theta is x. So we go ahead and start out with that step, and as we just noted, the left side is x squared plus y squared, and the right side is 4x. All right, so this is our Cartesian equation. Now I'm going to go ahead and rewrite this equation so it's in a more recognizable form. So I'll start out by subtracting 4x from both sides, and then I'll go ahead and complete the square on this quadratic expression in x. Okay, so I'm going to replace x squared minus 4x with quantity x minus 2 squared minus 4. And then I'm going to go ahead and add 4 to both sides of this equation, and this gives us a Cartesian equation for the circle of radius 2 centered at the point 2, 0. You see that circle down here. All right, great. Now for part B, it says more generally find a Cartesian equation for the curve r equals 2a cosine theta. Okay, well, we can do exactly the same thing that we did in part A. So in other words, multiply both sides by r. This gives us r squared, which is x squared plus y squared on the left, and 2a r cosine theta, which is 2ax on the right. And then I'm going to go ahead and subtract 2ax from both sides, then complete the square on this quadratic expression in x. And that gives us quantity x minus a squared. Add a squared to both sides, and we arrive at this Cartesian equation for the circle of radius a centered at the point a, 0. Okay, and we make a note here that part A is actually just a special case of part B. Notice that if I set this a value equal to 2, then I'll get a 4 cosine theta in this expression for B, and that's exactly what we were looking at in part A. All right, so let's go over real quick to Desmos. So Desmos will sketch polar curves for us, which is really nice. We'll make use of this in the next section as well. So here I've set a equal to 2, and you see that this is the circle we described in part A. Okay, now if I increase a, you can see, right, that's giving us a circle of radius a, and the center is at the point a, 0. So if a is 4.7, the center of this circle is at 4.7, 0. Now if we set a to a negative value, okay, now we're looking at this circle in quadrants 2 and 3. Center is still at a, 0. Here a is negative 6.4, and the radius is still a. All right, cool. So the last thing I want to mention here is the following. What if we were to replace the cosine of theta with a sine of theta? What would happen in that case? Well, we could just as well go through this same argument, multiply both sides by r. That's going to give us a 2ar sine theta, so we'd have a 2ay on the right side. Then we could subtract and complete the square. The bottom line is we're going to get a circle equation. Now I'll go ahead and plot that circle if you replace the cosine with the sine. Okay, and as we see here, this circle in green is just the circle in blue rotated by 90 degrees. And here if I change the value of a, okay, I get all of these circles here. All right, so why is that not a surprise? Replacing cosine of theta with sine theta, it's really giving rise to this 90-degree rotation. Well, that follows from what's called the complementary angle identity that you would have seen in pre-calculus, right? So sine of theta is really just the cosine of pi over 2 minus theta. And replacing theta with pi over 2 minus theta, that's going to give rise to a 90-degree rotation counterclockwise in the xy plane. So this phenomenon of replacing cosine with sine and seeing this rotation is more general than just when looking at these circle equations, okay? So if you take any polar equation that involves cosines and you just swap them out for sines, okay, that's just going to in turn rotate your curve 90 degrees counterclockwise. All right, well, that's a good place to stop, and I'll see you in the next video. Thanks.